This is Honors Algebra 2 Pre-Calculus. We're doing section 9.3 in Pre-Calc, which is, at this point, we're talking about the sum of an infinite geometric series, which is going to end up mattering a lot when we get to BC Calc the year after AB Calc. So the reason I write this a little different than you're going to see it in your book, and if you do look in your book, you're going to see this on page 638, right? So that's fine. So I want to clarify, I want to write two different versions of the same statement because I think that one way we sometimes fall for a trap here is because we don't realize that they're saying the same thing in a different way. So, in either case, so the textbook gives you that a geometric series starts plugging in I is 0, right, and goes up to infinity. And notice that that would make this first term an A, or an A sub 1, which is what your textbook writes, A times R to the 0, meaning the first term would just be A by itself, right? The other way to write this is that you don't start at 0, you start at I is 1, but instead of the R term being R to the I, it's R to the I minus 1. Notice that this, even if I write it this way, the same important piece of information is that the first term of this expression, wherever I start, which in this case was at 0, in this case is at 1, either way, wherever I start, what I plug in, I get A as the first term. Either of those infinite geometric series will sum to A over 1 minus R, but with a caveat, okay, if the absolute value of R is less than 1, okay? So this is only the case. So if the absolute value of R is less than 1, then this thing will converge to this number. So that's what we call it. We call it converging. It will sum to a finite number, A over 1 minus R. If the absolute value of R is greater than or equal to 1, then the series diverges, right? So a lot of AP BC Calc, a huge part of that year of your life, of that academic year, is going to be spent talking about whether a series, a sum of values, converges. So to converge or to be convergent means sums to a finite quantity, right? Sometimes we don't even know what finite quantity, we just know it sums to a finite quantity. To diverge means sums to an infinite quantity. So if this R value in its absolute value is less than 1, then this geometric series will converge to A over 1 minus R, to that finite number that we are able to find. If R is greater than or equal to 1, we cannot find this sum, and we just say that it is divergent or that the series diverges or any version of that. So that's sort of the gist. So now what we're going to do is we're going to go back and find the sum of the same series that we did in the last example, but this time instead of doing from 1 to 10, we're going to do it from 1 to infinity, right? So let's go back and find the sum. So in example 5, right? So in example 5, we used the sum from 1 to 10, but now we're going to do infinity, of a 5 times a 0.2 to the n, right? So now we're going to find the infinite sum. So the first thing to recognize is I still need to write out my first couple of terms because I need to know what that first term is. So when I plug in n is 1, right, I get 5 times 0.2, and just like we established the last time, that means that my first term, a, is a 1, right? And I can see that the thing I multiply every time is a 0.2, because this would be that 1 times another 0.2, and then the next one would be that 1 times a 0.2 times another 0.2, etc., right? So I say, oh, okay, cool, I can see that my R is definitely a 0.2, right? And I know that the absolute value of 0.2 is smaller than 1, so this value is going to converge. What that means is that this entire sum of all these numbers is going to converge to A over 1 minus R, which is A, 1 over 1 minus a 0.2, right? Well, that's a 1 over, and you can either make it a 0.8 or you can make it a 4/5, I don't care, right? So 1 divided by 0.8, or 1 over a 4/5 if you prefer, which means that this is a 1 times a 5/4 or a 1.25. And you may recall when we did example, so in example 5, we did the nth partial sum, we did up to 10, and we got 1.249 da 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 da, right? So if we only added the first 10 terms, we get something just a little smaller than this. And if we keep adding until we get to infinity, we end up getting a 1.25. So we're going to do an example 7. All right, so example 7, we're going to do a joke, okay? So we're going to do a joke about infinite mathematicians walk into a bar, Okay, so I'm going to tell you the joke. I'm not going to write the whole joke down because that's just miserable. Okay, so infinite mathematicians walk into a bar. The first mathematician orders a pint of water, full pint of water, right? So the first mathematician says, hey, I'd like a pint of water, right? And the bartender says, cool, gotcha. The second mathematician says, so this was a full pint of water, right? The second mathematician says, I'm not as thirsty. She says, I'll take a half a glass of water, okay? So we had a full glass of water, and then the next mathematician says, hey, I'll take a half a glass of water. And then the third mathematician, well, he says, I'm really not all that thirsty at all. I'll take a fourth of a glass of water, right? And then the next mathematician says, I'm even less thirsty. I'll take an eighth of a glass of water, right? And so on, right? Ad infinitum, right? Which means to infinity. So the bartender says, whoa, let me stop you there. Pours, so the bartender, right? Bartender says, all right, cool, I gotcha. Pours 2 full glasses and says, know your limits, ladies. Because in this problem, my infinite mathematicians are female. Anyway, so bartender tells a joke, and she says, ignore the alarm on my phone, she says, know your limits, and pours 2 full pints. So let's talk about why the bartender pours the 2 full pints of water, and how that mathematically makes sense, and why it's funny. So here's the idea. We have this 1 full pint already. That's a given, right? So the question is, how is it that the rest of the ones add up to 2? Well, you can actually visualize this pretty easily. So let's start with, so we're going to take this second glass, and we're going to kind of fill it up, okay? So if I take the second glass, I give the first person a half a glass, right? So half of the glass. That's that one mathematician. And then the next person says, hey, I want a fourth. Well, a fourth is half of the remaining space, right? Because half of the glass was full, and a fourth is a half of a half. And then the next person says, hey, I want an eighth. Well, an eighth is a half of the remaining space, right? A half of the remaining space, meaning that I still have another eighth left. And then the next person takes a 16th, which is a half of the remaining space. And then the next person takes a 1/32nd, which is a half of the remaining space. And then the next person takes a 1/64th, which is a half of the remaining space, until infinity. So what happens is they get infinitely close to filling that second glass, and mathematically they do fill that second glass. There's also a famous problem about Achilles and a tortoise, if you want to Google it. That's the same kind of idea. So now that we've seen the visual, let's see why it works mathematically. This is a geometric series, right? My first term was 1, and the thing I'm multiplying by is definitely a half, right? 1 times a half gives me a half, times a half gives me a fourth. So, based on what we know about a geometric series, this should converge to a over 1 minus r. That's a 1 divided by a 1/2, which is absolutely a 2. So that's why it's 2 full glasses.